Hello, bonjour, Chiara. I'm Adrian. It's July 11th, and this is AInVFX Deep Dive. Today, we're diving deep into video upscaling. It is such a challenging problem. Most solutions out there either flicker on video, are painfully slow, require massive GPUs, or expensive and closed source. All of this is about to change with SeedVR2, the latest breakthrough from ByteDance. They achieved high-quality video upscaling in a single step and released it to the community with a permissive Apache 2 license. We're going to break it down together so I can explain the model architecture and how to use it for free in ComfyUI. I'm going to go through all the parameters and what we implemented recently to run it on consumer hardware. I will also cover upscaling of image sequences with Alpha and how to support multi-GPU using command line upscaling. There is a lot to go through. Allez, c'est parti. Video restoration faces a fundamental challenge. Traditional diffusion models like Upscaler Video, MGLD, and STAR need 15 to 50 denoising steps to transform low-quality video into high-resolution output. Even the original SeedVR, which earned highlight recognition at CVPR last month, still requires multiple steps. SeedVR2 takes a different path. While it's built on the diffusion transformer architecture, it uses GAN training to achieve one-step video restoration. A GAN, or generative adversarial network, uses two competing neural networks, a generator that creates upscaled frames and a discriminator that judges if they look real, each trying to outsmart the other until the results become indistinguishable from real footage. ByteDance achieves this through adversarial post-training, or APT. They start with SeedVR, their pre-trained diffusion model, as a stable foundation. Then they train it adversarially against real data, transforming it into what they call the largest ever video restoration GAN at around 16 billion parameters. This hybrid approach combines diffusion's reliable starting point with GAN training's ability to produce more realistic details. APT works in two stages. First, they gradually compress the process using distillation. The teacher model shows the student model how to go from 64 steps to 32, maintaining the same quality. Once mastered, they compress to 16, then 8, and finally one step. It's like teaching an artist to paint the same portrait in half the time, then half again, until they can capture it in a single brushstroke. Second, they train on real videos. Traditional distillation involves the teacher model generating thousands of upscaled video as the training examples for the student to copy. But this has a ceiling. The student can never exceed the teacher's quality. Here, they collect real high-resolution videos, degrade them to low quality, then train the model to restore them in one step. With this approach, the student can actually surpass its teacher. Temporal consistency emerges naturally from the progressive training approach. They start with single images, then gradually train to longer sequences, teaching the model to balance sharp details with smooth motion across time. Let's dive in ComfyUI to see this in action. First, we're going to go into our custom node manager and make sure you have the latest version of SeedVR2 from NumZ. Definitely grab the latest version because we have just added support for BlockSwap and we're going to be using it in that demonstration today. The other packs that you'll need will be the Video Helper Suite. We're going to be using that one to load and save video. And we're also going to be using the CocoTools IO from our friend Connor to make sure we can save our video into a sequence of images with Alpha. Once that is all installed, make sure to reload ComfyUI and let's get started. To use SeedVR2, it's very simple. You don't need much. So let's start by loading a video. Let's use a load video upload. And I'm going to grab one of my examples that I will add into the GitHub repo if you want to play with the same footage. They're all clips from Pixels. So here I have a low quality close-up of some eyes, and we're gonna use that for our testing. Just for now, I'm gonna start with a single frame. Then we're going to be using a SeedVR2 video upscaler. Image goes into image. And we're going to use a video combine for the output. Image goes into image. Gonna keep the same frame rate, 25. And save that as H264 MP4. Now, I'm going to reduce the target resolution. So this is the shortest edge of your image. So in my case here, I have a clip that's 212 times 120. I'm going to start with 480, which is a 4x upscale. Let's run the generation. What's happening here? We're running out of memory. And what you will soon discover is that SeedVR2 is very hungry for VRAM. But don't worry about it. We're going to find ways to work with it. So one thing we can start doing is take that option here, which is preserve VRAM. What preserve VRAM is doing is to offload the diffusion model after each batch and offload the VAE after each decoding process. And by offloading, we're releasing the VRAM that's currently sitting on the GPU. So instead of keeping everything on the GPU VRAM, each time one process is done, we bring it into the CPU RAM and we clear the VRAM. And as you can see, we were able to upscale that image. If you look at the quality, it's actually pretty nice, and it was also reasonably fast to run. If this was the first time that you were using SeedVR2, you would have downloaded the model for you at the beginning, so it's not something that you have to do manually. What parameters do we have on the node that we can play with? First of all, we have the model parameter, where we can pick which model we want to use. SeedVR2 comes in two different size, 3 billion parameters and 7 billion parameters. As a rule of thumb, I'm going to be using the 7 billion parameters because it tends to do a better job with heavily degraded video and also AI generated videos. However, if you care about speed, go with the 3 billion parameter, that is faster to run. If I were to start a generation right now with the 7 billion parameter, it's going to run out of memory because I do not have enough VRAM on my machine. But don't be worried, I'm going to show you how you can still use that model even if you don't have a lot of VRAM. For reference, I'm using a laptop at the moment with a 4090 RTX with 16 gigs of VRAM. And here you go. So I'm going to go back to the 3 billion parameter model for now. The other thing to keep in mind is that there are two different precision available, FP8 and FP16. Now, pay attention. You would think that FP8 model is going to use less VRAM than the FP16. In that case, it is not true. In the current implementation of SeedVR2, the FP8 models are being converted to BF16 to resolve a compatibility issue. What that means is that additional conversion process ends up using more VRAM in the end. So if you care about VRAM and quality, use the FP16 model. If you care about speed, use the FP8 model. To summarize, if you care about quality and VRAM, I highly encourage you to use a 7B model with FP16 precision. If you care about speed, go back to the 3B FP8. For now, while we're testing on images, I'm going to stick with the 3B FP8 and I'll move to the other one after. Then we have the seed parameter. It's going to affect the determinism of your generation. So if you don't like the specific details of your frame and you want to try a variant of it without changing too much, you can just play with a different seed. Because we're doing an upscaling process that is true to the original image, it's not going to be a huge variation between two seeds. But if you think small artifacts, you can still try to resolve them by changing seed value. Just to make things easier to see, I'm going to load the individual frames so we can compare them. The changes between the two are very small, okay? It's just high frequency details. Then we have the resolution setting. So as we mentioned earlier, this is going to look at the shortest edge of your final image. So right now, my shortest edge is a height, and I have 120 pixels on the height. So because I'm doing a 480 resolution upscale, so I'm doing a 4x upscale. The batch size is only going to affect upscaling when working on videos, and it's going to say how many images are we going to upscale at once. And as a rule of thumb, you want that batch size to be the highest possible number while not being greater to the amount of images that you have in your input video, and while making sure you don't run out of memory on your machine. Having a large number is important here because it's going to make sure that your upscaling is also temporally consistent. In other words, we're going to make sure that we don't have any flickering in your generated video. The batch size needs to be a multiple of 4 plus 1. We will go back to that in a moment when we talk about video. And then we have the preserve VRAM parameter that we already introduced earlier that makes sure that we free up the VRAM after each process so we can run this model on consumer hardware. What about video upscaling? First of all, we need to increase the amount of frames that we're loading here. Let's start with 40 frames and let's run the generation. Just to make sure you don't end up waiting, I'm going to speed up the video and I'll see you in a second. The first thing you can see here is that it's not as stable as it could be, okay? If we compare with our original footage, there's quite a bit of flickering in the high frequency details. And that's coming from the batch size value. At the moment, we're only processing 5 frames at a time. And because that video is 40 frames long, it does lead to some flickering. If you want something that is more stable, we need to increase that number. And ideally, you want it, as I said, to be the highest number possible. If we go all the way to, actually, let's go 45 and let's make our input video 45 frame as well. If we do that, we're going to upscale all the frame at the same time. And so the model is going to make sure that the result doesn't flicker. And now we run out of memory. And that's going to be very frustrating. So to resolve that problem, what I've developed this week is BlockSwap for SeedVR2. Let's add another node, which is SeedVR2 BlockSwap config. And what you're going to do, you're going to plug that one into the BlockSwap config input of the SeedVR2 Upscaler. You have a few parameters that you can play with. The first one is block to swap, and that's going to define how many blocks we want to have on the GPU. In the context of transformer architecture, blocks are the fundamental building units that stack on top of each other to form the complete model. Think of it like a skyscraper where each floor is a block that processes the data and passes it up to the next floor. In SeedVR2, the 3B model has 32 blocks, so it's like a 32-floor building, while the 7B model is a 36-floor building. Each block contains 3 key components: an attention mechanism, where the model decides what part of the image to focus on, feed-forward neural networks that transform the data, and normalization layers that keep the numbers stable. When you process an image through SeedVR2, it goes through all these blocks sequentially. Block 1 processes it, passes the result to block 2, which processes it further, and so on until the last block. With BlockSwap, instead of keeping all 32 blocks in GPU memory at once, we only keep a subset. We store the remaining ones on CPU RAM. When we need them, we quickly move them to the GPU, do the computation, then move them back. This way, you only need VRAM for the blocks you're actively keeping on the GPU at a given time. This is what allows us to run these large models on consumer hardware. So as we said, we have 32 blocks on the 3B model, so we're going to bring that number here to 32 to offload all the blocks on the CPU RAM. The use non-blocking parameter is going to allow asynchronous transfer between CPU and GPU, making the process faster. There is little downside by using it. It might be using slightly more RAM at some point, but I will encourage you to keep it true to make your processing faster. The offload IO component is going to allow you to offload the input and output embeddings that we're using for the generation. So think about your video input that we're using. It's going to allow you to save a bit more VRAM if you're really struggling with resources. The cache model parameter is going to make sure we keep the model cached in RAM after a generation. So if you're planning to run multiple generation, what you'll find is that at the beginning of each generation, there is a delay where we're waiting for the model to be loaded. That's painfully annoying. So to avoid that problem, we can turn on cache model, and we'll make sure that we're always going to have the model available each time that we need to do a generation. And then we have a debug option that allows you to output everything that the BlockSwap config is doing into the shell if you want to better understand the process, or if you also want to monitor your memory usage. If you forget what the parameter does, have a look at the documentation. I try to explain everything here, so hopefully that will make sense. Let's try rerunning the generation now that we have BlockSwap config on. What do we notice? First of all, we didn't run out of RAM, so that's a good thing. We have an upscale video. The other thing that we can see is that it is stable. Okay, we do not have any of the flickering that we had earlier, which is great. So if you compare our input with our output, it's quite a nice transition. If you look at the logs from the process, you can see here, because we've turned on enable debug true, you see what's happening. You see all the blocks. So as I said, we have 32 blocks. So we're going from 0 to 31 of that model. And we see all the blocks being swapped from the CPU to the GPU. Okay, and you have the time of swapping for each block. And then we also see the inputs embedding and outputs embedding also being swapped. Now that we have BlockSwap on, I'm going to make myself happy and use a FP16 model. Because I've changed model, if I rerun that generation and I look at the logs, it's going to say that the model changed, so it's going to do a full cleanup and load that new model. And now we're able to work with our higher quality model. If you look at the quality, it's actually really good. Let's sync that. There's a lot of details in there. Now, I was telling you earlier that the 7B model has 36 blocks, but we've only used 32 here. So you might be asking, why are we not using 36? Well, the reality is you don't want to use BlockSwap if you don't have to. If we go back to the logs, each time we're swapping one block, we're adding some additional overhead on the overall processing time because we need to account for the transfer from the CPU to the GPU and back to the CPU. So if you're fine with your VRAM, don't increase that number. However, if you're running out of memory, feel free to increase that number. What I like doing is to start by disabling offload IO component and have a lower number of block to swap, let's say around 16, then run a generation. If I run out of VRAM, then I'm going to increase it and run it. And all the way to 36, which is the maximum number. And then if I'm still out of VRAM, I'm going to turn on offload IO components. But if you're fine without it, keep those numbers lower so you don't end up waiting longer than you have to. Now, if this was my final generation, what I would do is I would complete the process with an upscale image. And then I will go all the way, let's say to HD. And I'm going to use NumZ as a filtering that creates picture with sharper details. And here you go. You have your upscaling process from 212 times 120 all the way to Full HD. One thing that would be interesting to do at this stage is compare with our ground truth. So to generate that video, I actually used a higher resolution video that I've done sampled. So out of curiosity, let's load it now and see what we have. So if we compare with our ground truth, which was that one, what we realize is that SeedVR2 tend to add a lot of details, and sometimes it is too much details, it's too sharp. That might not be what you want. There used to be a setting here, a CFG scale setting that we could dial to say how much enhancement we want. And if it was overly sharpened, we could use a number to bring it closer to our input. Unfortunately, that setting has been disabled at the moment because there is an issue in the original implementation. So what if you still want to upscale your sequence in HD, but you don't want to have so much details? But first of all, let's set our seed to fixed so we can work with something that is consistent across our various tests, and also that will make sure that that node is not recomputed each time I'm going to press run. Because otherwise, if we set it to randomize, each time we're going to press that run button, it's going to change the seed and then rerun that process. Let's duplicate that workflow here. And what we're going to be doing is that instead of doing an upscaling for X, which was for 80, because our input started at 120, we're going to do a 2X only, so 240. Instead of using a sharp filtering like Lanczos, we're going to be using a softer one like bilinear or bicubic if you want an in-between. Now let's rerun that generation. Actually, let's save the scene. And if we sync the preview, so we end up with something that's a bit softer. If we look around the eyes, it is not as defined as we have here. It's not perfectly matching our ground truth. Our model doesn't know what our ground truth look like, but that still gives you a way to adjust how much details you want to get in your final pictures. Let's bypass this output for now. If you don't work with video and you only want to work with images, you can push the upscaling much further. Of course, if you have a lot of VRAM, you can push also the upscaling for video generation much further. But because I'm limited here with my machine, I'm not going to go higher than 4x. Let's do a quick test with pictures. So if I duplicate that workflow again, and we're going to go back to only one frame. Let's offload the entire model, and we're going to try a 10x upscaling. So from 120 to 1200. I'm going to remove that upscaling node for now because I'm doing straight high quality upscaling from SeedVR2. And now let's render that generation. If we look at our final image, we've been pushing the details quite a lot. It's really up to you what look you prefer. Higher upscaling out of SeedVR2 doesn't necessarily mean more realistic render. Okay, so you definitely need to play with those numbers. As a comparison, if we try 5x upscaling, we go 600. So you have 5x on the left and 10x on the right. The features are different. If you see on the left, like we see a bit more of the wrinkles that we tend to lose more in the 10x upscaling. And if we go back to our 4x upscaling, actually that was a 2x, so it's very soft, and the 4x is a bit of an in-between. So at the end of the day, what I encourage you to do is to use a traditional upscale image node just before your final output, set that to your desired resolution, and then put the SeedVR2 node in between and try different upscale resolution until you find one that gives you the look that you're after. Let's take a moment to talk architecture. Under the hood, SeedVR2 uses a Swin transformer, short for shifted window transformer. Traditional methods rely on patch-based sampling, dividing videos into overlapping tiles with up to 50% overlap just to avoid visible seams. What makes Swin transformer unique is its attention mechanism. It takes the entire video frame as input and divides the processing into windows, different focus area within the neural network. These processing windows are adaptive, meaning they are dynamically resizing based on your target resolution. This allows the model to work well at any output resolution while avoiding processing seams and artifacts. To stabilize training, they employ several mathematical guardrails. RP GAN loss prevents mode collapse to avoid repetitive outputs. R1 and R2 regularization keeps the discriminator from becoming overconfident, ensuring both neural networks improve together. Feature matching loss measures quality directly in latent space, avoiding the expensive pixel space calculations. I've reorganized the scene a bit if you want to use it as a reference so you know what is what, and I've added notes on the side. Just keep in mind that when I say 2x upscaling, that's based on my input resolution, okay? So here I have 120 as the shortest edge, when I do go to 240, it is a 2x upscaling. But if you start with a video that's already higher resolution than that, you need to increase that number. Otherwise, you're going to downscale it instead of upscaling it. Okay, so now what do you do if you're working with image sequences, and especially if you're working with image sequences with alpha? Let's give that a go. We're going to be using a load images upload. And here we can pick a directory. And I've already created a dog directory in my input folder for ComfyUI. But in your case, you can use the choose folder to upload if you want to pick a different image sequence. So if you look at your load images upload node, you have two output, image and the mask. So what we're going to be doing is we're going to grab our SeedVR2 video upscaler, do one for the RGB, another one for the alpha. We're going to make sure we pick the model that we like for both of them. The same model, we're going to use the same seed, we're going to make sure it's fixed. We're going to set our resolution. Here, my shortest edge is 240, so I'm going to go 480 to do a 2x upscaling. I can also link those parameters if I wanted to make sure they remain the same. The byte size, I'm going to put it as high as I can. Let's try 45, which is the amount of frame I have in that video. I'm going to keep my preserve VRAM at true. And I'm going to add my BlockSwap config. I'm going to increase that number all the way to 36 because my input video has a higher resolution than what I was working earlier. So I'm predicting that I'm going to need more VRAM. And I'm going to turn on cache model and the debug. For now, I'm going to leave the offload IO component first. I'm going to see if I can get away without using it. Then we're going to take both images output and we're going to have to merge them back together in a final image. But first, we need to convert that one into an alpha channel. So we're going to do image to mask. Doesn't matter which channel you pick because they're all the same, which makes me think that I've made a mistake here. If we are scaling the alpha, we need to make sure we grab the mask and not the image. So we need to do the opposite here. We're going to do a mask to image and then go into the SeedVR node. So here we have one channel for the alpha, and then we copy the same channel into RGB. And that's why I'm saying it doesn't matter which one you grab here because they're all the same. Then at this stage, we need to merge those two back together. So we're going to do a join image with alpha. Image goes into image, mask goes into alpha. And then we're going to write out this as an image sequence. And for that, we're going to be using the great Coco tools from Connor. Let's do it. Coco Saver. Image goes to image. We're going to set our file path. You put whatever you want. For me, that's a folder I've created earlier. You can set the file name. And I'm going to save that as PNG 16-bit. That's fine. But if you wanted to, you could go to EXR and different compression level. Like you could go all the way to XR 32 bits. Let's stick to PNG 16 for now. And I'm also going to make sure I add an upscale node just before the final output. I'm going to go to longZOS for that one. The input resolution, I'm going to go all the way to 1280. 768. Let's run the generation and see what we get. And we run out of memory. That happens. We can try to offload the IO component, and we're also going to disable caching because we are only doing one generation anyway, just one batch of 45 frames all at once, and then we're done. So there is no need to cache the model here. Let's give that a go. And that went through. At the moment, the Coco Saver node doesn't give you a preview. So if we want to see the result, let's add a load images upload. And we're gonna grab our Upscale folder. This is just a 2x upscale, so there is definitely room to push that further. But if you look around the eyes, you already see the added definition. When you are running generation with SeedVR2, you're going to run into memory issues, so that's definitely something to watch out for. At the moment, the current BlockSwap and caching mechanism are not perfect, so there's still a bit of memory leakage here and there that I need to fix, but hopefully that will still give you a good foundation to get started even on consumer hardware. If you run into any issue, as we've seen, try to increase the amount of block to swap. You can try to offload the I/O component. If you don't need caching, if we're just doing one generation, disable it. And as a last resort, you can also completely relaunch ComfyUI to completely purge the memory from your system. Let's look at results from different sources to see where SeedVR2 shines and where it struggles. Keep in mind these release models are prototypes that may not fully match the paper's reported performance. Heavy degradation or rapid motion still challenges the system. On clean content, especially AI-generated video, the model sometimes adds excessive details, creating an over-sharpened look. While the sampling process is fast, a significant amount of computation time is spent on VAE encoding and decoding. According to the test, the VAE can account for up to 95% of the total processing time. Even though the entire process remains faster than other solutions, there is still room for performance improvements. Memory consumption is also high. Even the 3B model demands more than 16 GB of VRAM. To compensate for this, use preserved VRAM and the BlockSwap technique we demonstrated earlier. We're also looking into adding support for VAE tailing in the future. For multi-GPU processing, NumZ released the command line interface tool that can be used as a standalone to distribute frame across multiple GPUs. For example, with 4 GPUs and 1000 frames, each GPU processes 250 frames in parallel, dramatically speeding up large jobs. You'll find all the details explained on the GitHub repo. That's it for today's episode. Thank you to Biden for sharing their research, model, and code with the community under an Apache 2 license. And thank you to NumZ for the excellent ComfyUI integration. Together, they made high-quality video restoration significantly more accessible for all of us. You'll find all the links in the video description, so please give the GitHub repo the stars. If you learned something new today, like and subscribe. And if you have any question, let us know in the comments. I will see you again next week for another episode of AInVFX. Thank you for watching.